It's an honor to be here and to be able to give this talk. So I am part of the team that is supporting the systems side of LLM-JP development, and I have a HPC background. So my talk will try to focus on the architecture side. So we are also responsible for keeping up with the latest architectures and getting them to scale on our systems. So mixture of experts models have been around for quite a while, but the sparsity of recent models is increasing. As you can see here, Qwen3, Kimi, GLM, DeepSeek, GPT-OSS are open models, open weight models that are that have good performance, and they all have, as you can see here on the experts column, a very large number of experts, and only a few of them are active. This is very good for reducing the training and also inference cost. And also, as you can see on the bottom figure, they're very competitive now with frontier models. And of course, there's some talk that this is, these models are tuned towards these benchmarks somehow, but still, they are able to achieve these scores. So that itself is impressive. Now, there are scaling laws for MOEs as well, and in particular, this paper called Parameters versus Flops investigates this kind of scaling with respect to the sparsity. So, as you can see on the left figure here, the optimal sparsity increases with the total parameters. So this means larger models should be more sparse, right? You get the optimal sort of pre-training loss if you are using more sparse models. As the size increases, you need to use more sparsity. The other thing you can see from the right figure is that the optimal sparsity mildly decreases with the active parameters, but still the increase with the total parameters is a much steeper slope. Also, the green line indicates the most sparse model that was tested. And this, as you can see, for the optimal sparsity, it gets the lowest pre-training loss. So the most sparse model is achieving the lowest loss, regardless of the model size here. So then there's another interesting recent work that investigates what kind of dependency does the sparsity have on the downstream tasks. And they roughly categorize the downstream tasks into memorization and reasoning tasks. And this balance, as you can see in these figures at the bottom, is very interesting, actually. So when you fix active parameters and increase the total parameters, this means fixing the cost and increasing model capacity. For the memorization tasks, like the one that's on the left that says world knowledge, this is trivia QA and a bunch of other, it's an average of, I think, a few downstream tasks. And you can see for the world knowledge tasks, the accuracy actually does increase with total parameters. So that means you can fix the training cost because active parameters are constant here, and you can just keep scaling up the number of experts. And you achieve better F1 accuracy on these memorization tasks. And the one in the center, the common sense tasks, these are, you can think of tasks like HelloSwag, but this is also an average of, not just one downstream task, so it's an average of a few. But this one is somewhat in between, right? And then on the far right, you have math benchmarks. And for this case, it's obviously not scaling with the number of total parameters. For more sparse models, the score is noticeably lower. And so is sparsity not good for reasoning? This is a concern that we had because, as Professor Kurohashi mentioned in his talk, we are going to be training these very sparse MOEs soon. And we wanted to get this part right, especially because reasoning is an increasingly important downstream task. So we did some experiments, and we used Mixtral as a base model. We used the standard normalization, activation, and positional embeddings that people commonly use nowadays. And we tested with different model width, number of experts, and activated experts. And you can see the different colors in these figures. They have different combination of these parameters. And they all seem to show a similar trend. As the total number of parameters increases, the loss decreases. And but this is just looking at the training loss and validation loss, not the downstream tasks. Now, if you look at the downstream tasks accuracy and compare that with the training loss, ideally, we want the downstream accuracy to inversely scale with the training loss. So as the loss decreases, we want the accuracy to increase, so have a slope like this. And for Trivia QA and HeliSwag, we see a very clean line here. However, for the math task, GSM-8K, we don't see this kind of a clear trend. And also you see at the left part of the figure in the pink and purple parts, you actually see inverse scaling. And this is it actually matches with what was reported in the mixture of parrots paper. And so we did confirm this independently, and also we tested with, after doing test time compute, and also with some reinforcement learning with GRPO, and we still see this trend. It shows this inverse scaling. So also, another interesting thing we found along the way is that instead of plotting, the previous figure was plotting against the final training loss. But then if you change that to the tokens per parameter, okay, so chinchilla scaling law says that you need roughly 20 tokens per parameter. But following, more recent research has shown that the optimal TPP is task dependent. It depends on your downstream task, which is exactly what we are trying to look at here. And the memorization task in this paper, not our results, in the Roberts et al. Paper, they say memorization benefits more from lower tokens per parameter, and reasoning benefits more from higher tokens per parameter. And what we see here is by plotting against a TPP, so let me go back one slide. In the GSM-8K figure here, this looks like a trend with inverse scaling at the end, and you don't really see the colors being aligned. But if you look at this figure, when you plot against TPP, especially the GSM plus shows this clear alignment of the peak value here. So somewhere around like 20 to 30 tokens per parameter, it seems to peak. And this doesn't seem to depend on the model size or the sparsity. And so this reveals some interesting ratio balance that we may want to consider when we start training our MOEs. We actually have my student is presenting a poster on this topic. So if you're interested, please come by and ask my student difficult questions. Thank you.